In this lecture, I'm going to try to give a brief overview of classification methods. This is quite a broad field and complex, so I will skip some details and give you just a general idea. And for that, I'm going to focus on two different classification algorithms, logistic regression and support vector machines, because I can use them to illustrate some important points about that idea of expanding features into higher dimensional space with nonlinear transformation as a way of improving the power of our models. So what we did with the linear regression and expanding to polynomial regression, we can do that also in classification. So I'm going to start to talk about this difference between regression and classification. Then we're going to see logistic regression that illustrates this relation because it's actually a regression, but we use it as a classifier. And then support vector machines, because the support vector machine is a very powerful way of doing that nonlinear transformation to a higher dimension that we can use to increase the power of the classifier. So let's start with this notion of separability, that we want to separate classes, and we can say that the classes are linearly separable if we can separate them by something that is straight, a linear discriminant. So basically a linear combination of the features. In 2 dimensions, this will be a straight line. In 3 dimensions, a plane. In many dimensions, a hyperplane, but it's a linear combination of the features. And so we call this the linear discriminant, and sometimes we can find data sets that are not linearly separable. So at least in this space, the linear discriminant would not be able to separate these classes without errors. But we'll see how we can improve that using those transformations. But the general idea that we want to start with is that we want to separate our data into different regions. So the space where our points lie will be partitioned into different regions. So in regression, we defined this straight line that we wanted to fit to a set of points with 2 parameters. We wanted to predict this y as a function of x, so we defined this straight line in these dimensions with the slope and the intercept. Even though we are using a straight line to try to classify these points, we need something more, because the line itself does not tell us on which side is which class. So we actually need something a bit different, which is to use a vector that is perpendicular to the discriminant and points in the direction of the positive region. So this expression, if we consider this in some arbitrary number of dimensions, this would be the coordinates of a point, this x vector. This is the vector w that defines the direction where the positive region lies. So if the x point is on the same side, this inner product between the two will be positive, and so we have the positive side of the plane. So looking at this in 3 dimensions, if this vector w is pointing this way, then this region here is the positive region, because any point here will have a positive inner product with this vector. Then on this side we will have the negative region, and the set of points where this equation is true, where the expression here is 0, is the discriminant. So it's, in this case, it would be this plane which is exactly separating the 2 regions, positive and negative. So this way we can split the space where our data lies into the different regions corresponding to the different classes. So we have the frontier given by this function. We have this perpendicular vector multiplied by the inner product with any point plus this intercept, and this is the function that is 0 at the discriminant, positive on one side and negative on the other. This way we can distinguish between the different regions. But now the question is, how do we find these parameters, the W and W0, so the W vector and the W0, to determine where we put the discriminant? So one wrong answer for this would be to use the least mean squares method that we used before, so minimizing the quadratic error. We could try to fit these parameters in such a way that this function that is negative on one side and positive on the other would minimize the quadratic error to the target labels of our classes that could be +1 on one side, -1 on the other. However, if we do this, we have this problem here, that we get a very bad result, because when we are trying to minimize the quadratic error, these points here that are far away from the frontier will be pulling the line so as to minimize the error there. And these ones will be pulling on this side. But actually, so this is actually what we want when we do a regression. We want our line to be pulled by the points that are farther away. We don't want to have those large errors. But this is exactly the opposite of what we want in a classification. Because if we think about the problem here, if we draw a line separating these points from these points, which are the ones close to the frontier between the two classes, the rest of the points are really irrelevant. They are on the correct side. Doesn't matter where they are, because they won't change the position of the frontier. So we want precisely the inverse of this. We don't want the least mean squares minimization, because that will cause points away from that are far away from the frontier to affect the position of the frontier. We just want to look at the points that are close to the other class and close to the discriminant, and those will be the ones that are relevant here. So this is good for regression, minimizing the quadratic error, but there is a fundamental difference between regression and classification. In regression, we want to fit our model as close as possible to the data, so to predict those values. In classification, we want to partition the data into different regions. So we don't want a line that is close to the data. We want a line that cuts between the two classes. So let's see logistic regression as one way of solving this. Let's assume that there is a function g. We don't know what function it is, but it's a function of the features, the x value, and some parameters that we can adjust. So this is a vector with a set of parameters. And this function tells us the probability of a point with those features belonging to class 1. So this function varies from 0 to 1, and it gives us this probability. We want the hyperplane, the discriminant, to be at the points where the probability of belonging to class 1 is the same as belonging to class 0. That is 50-50 on either side. So on one side of this discriminant, it will be more probable to be assigned to class 1. On the other side, it will be more probable that the points are class 0. And the discriminant lies exactly where the probabilities are the same. So we have this vector, the features. Based on those features, we can choose the class with these probabilities. And one way of trying to model this, so this function that gives us the probabilities, this should also be a function that varies between 0 and 1, because that's what probabilities are. And to solve this, we can use this, transform this equation like this. So take the logarithm of the probability of belonging to class 1 divided by 1 minus the probability of belonging to class 1 and equal this to 0 to find the place where we put the discriminant. Now the reason for this is basically that if we do it this way and we decide that we want a linear discriminant, so this logarithm of this fraction here will be positive when this term is larger than this one. So there's a higher probability of belonging to class 1. or negative when the probability of belonging to class 0 is higher. So this basically it's 0 at the discriminant, positive on one side, negative on the other, and this is what we obtain also if we use this linear expression with the perpendicular vector that points to one side. And this all matches up nicely, because if we solve this, then the function that we want is actually this function of the this linear expression here, and this is the logistic function. So basically it's this S curve that varies between 0 and 1. So this is the function that we are using to predict the probability of a point belonging to class 1. It's a nice function because it goes from 0 to 1, exactly as we want with the probability. The term that we have here inside the exponent there will be the expression for the linear discriminant. And this linear discriminant corresponds to where the probability of belonging to one class is equal to the probability of belonging to the other. So when this is the same as this, and so the logarithm goes down to 0, and that's where we are drawing the line. So this is the expression that we're going to use for logistic regression, and it has this nice property that, unlike with the quadratic curve that increases the further we go away from the frontier, so it starts to increase the error and is pulled by the points that are far away from the discriminant. The logistic function goes from 0 to 1, so we have, if we set one class to be class 0 and the other to be class 1, this works out nicely because it's just basically the classes that we have on one side and the other. And if we go far away from the discriminant, this is just a level function over here. So how do we find this by maximum likelihood? I'll just go briefly through these equations, but the idea is the same that we saw before. The likelihood of our parameters given some data set is the probability of the data assuming the parameters. So the parameters determine this function, g, that gives us the probability of belonging to class 1. And so the probability of our data set is the product of the probabilities of all data points. And we can compute them this way if our classes are 0 or 1. So the probability of belonging to class 1 raised to the class times the probability of not belonging to class 1, that is belonging to class 0, raised to 1 minus the class. So if the class is 1, it's this term here that counts, because 1 minus 1 is 0, and anything raised to 0 is 1, so it doesn't change here in the product. If the class is 0, then it's this one that is counting, and we are multiplying all these probabilities that our function is giving us for the points to belong to each class given their features. So this is what we want to maximize. We can take the logarithm so that we do away with the product, and we get this expression here with the logarithm. And basically we want to maximize this, so we want to minimize this, which is the symmetric of this one, and just averaging over all the points. And this is the logistic loss, or the cross entropy. So this is something similar to what we did with regression, only in regression we were assuming a Gaussian distribution of the error that is affecting the variable we're trying to predict. In this case, we are assuming these probabilities of belonging to class 1 or class 0 to estimate the probability of the data, but the reasoning is basically the same. So this is what we want to minimize, where the function is the logistic function applied to the discriminant with these parameters. So let's see an example of doing this. We're not going to actually implement this way, but I'm going to load the data and then standardize it. This, by the way, is something we saw briefly with the polynomial regression, but is important in general in classification for several reasons. when you have different features, so in general, if you are dealing with multivariate data, the different features can have different units, different scales, and so it may be useful to put everything on the same scale. So rescaling everything so that the distributions have a similar range. This makes it easier to adjust meta parameters because we are always dealing with the same orders of magnitude, and it's especially important when we are using methods that are more sensitive to distance or to vector products or things like that, where scaling of the features are important. So what we can do, standardization, is simply we compute the mean values for all the features, the standard deviation, and now we transform our data, we rescale it by subtracting the mean and dividing by the standard deviation. So since we are using, sorry, I have this extra here. Since we are using NumPy, we can use broadcasting. So this is actually a matrix with all our features. We take the mean on the 0 axis, so the direction of the rows. This will give us a vector with the mean for each column, with the standard deviation for each column, and now we are subtracting the means for each of the column and dividing by the standard deviations. So this will make all the features be distributed in the way that they have a 0 mean and a standard deviation of 1. So they are basically in approximately the same scale. Now, ideally, if we want to be very rigorous, and sometimes we need to do it this way, we should compute these scaling factors in the training set and then apply the same scaling factors to validation and test sets. However, since the mean and the standard deviation converge very rapidly when we have many points, in practice, this will generally not make a difference. So if you separate training, validation, and test sets at random, the mean and the standard deviation you compute will be probably very, very close to each other, if to the same value, whether you compute them only on the training set or if you use the whole set. So in many cases in practice we just rescale the whole set once and don't worry about this anymore. However, you should bear this in mind, because if there are some situations where, for example, you are using data from some time range and then trying to predict the future, or using data that is stratified, you have data from CTA, CTB, CTC, and you want to extrapolate to some new city, then you have to be careful, because this premise may not hold, and so it may be necessary to when you're testing your models, to use the same scaling parameters you computed only on the training set and apply those to validation and test. But for these problems here, we'll just assume that this is not a big deal, so we'll just get rid of this step in one go and then use the standardized data. So now we're going to fit the logistic regression classifier. You can import this from the linear model module in scikit-learn. You have the logistic regression class. We create an object for logistic regression. In this current version, if you don't specify the solver, you get a warning message, but it's no big deal. It uses the same solver. This tolerance factor specifies when to finish the computation, but you can omit it. This is a regularization parameter. I'm going to talk a bit more of that in the context of support vector machines. But basically, if you set it to a very high value, you are using almost no regularization in this case. If you set it to a lower value, then you increase regularization. Okay, so now we fit the classifier by providing the features matrix and the class labels. And now we get this result, which is better than what we had with the least mean squares. But now if we have data that is not linearly separable, we can still do the same thing. We can fit the classifier, but now this linear discriminant will not be able to properly separate our data. So there is a point here that is misclassified. But we can solve this problem by doing the same trick that we did with linear regression, which is to expand our features non-linearly. So imagine that we take the matrix with these values, so this gene activity here and this one here, these are the x values, x1, x2, and we add a new term here, which is the product of the two. So this is one example of a nonlinear expansion for this data. And now we have our data in 3 dimensions. We have the original two features plus the product of the two features. So we increase we increase the dimensionality of the features. Now we fit with the logistic regression, and what we are doing is now fitting not a straight line in 2 dimensions, but a straight plane in 3 dimensions, because this is the distribution of points that we get when we add as a 3rd dimension the product of the first 2. And since this is a nonlinear transformation, the points are now distributed in a bent surface in 3 dimensions. So when we cut this bent surface with a straight plane, the intersection between the two, the bent surface and the straight plane, is actually a curve. And so this is what we get here if we project everything back into the original 2 dimensions. So by doing this transformation, we can now use the linear classifier in higher dimensions, and in the original space it appears to work as something that is not linear, that does these curves. So this is the same thing that we did when we went from linear regression to polynomial regression. So expanding more, we can add more features, more expansion, and we can keep increasing the power until we have this the ability to fit our training data. And we can even go beyond that, and eventually we may get well into overfitting. For example, this red region here is quite a bit suspicious. There is no intuitive reason for predicting red points in that place. So as we did with regression, we can expand our data for classification with nonlinear transformations, and this increases the power of our classifier. So logistic regression is a special case of a classifier that actually is a regression, because it's even in the name, because we are fitting our function to predict the probability of belonging to a class. So this is we're trying to adjust the parameters to approximate as much as possible the probability of belonging to a class. But we use it as a classifier because we determine that we have this threshold of 50% for each class where we separate the two. The same way that we did with linear regression, we can also increase the power of this classifier if we expand non-linearly the features that we are using. However, logistic regression is not ideal for this because we need to do the expansion manually. And so we pay the computation costs of the expansion. We need to have everything in memory, and so it's not the best way of doing this. If we want to do this kind of thing, then it's better to use support vector machine. The idea of a support vector machine is to try to find the discriminant by maximizing the margins. So the margin, we have a margin classifier if we can measure the distance to the discriminant. So for example, that hyperplane separating the classes, and the maximum margin classifier tries to find the discriminant that maximizes the margin. And the margin is the distance to the nearest points. So these would be called the support vectors, because these are the ones that force the discriminant to be in that place. So using the original data set that we saw a while ago, we have these points here that are not really relevant. No matter where they are, they do not change the position of the discriminant. But these 3 points determine that the discriminant has to be here, so that the distance to the nearest points is as large as possible. There is no way to put the discriminant that would maximize or give us a greater distance to the nearest points. And once the discriminant is stuck here by these support vectors, the others don't really matter because they are further away from the discriminant, so they are not determining where the discriminant must be. So this is the basic idea behind the support vector machine. We want to identify these support vectors, which are the vectors that lie closest to the discriminant, and we want to maximize the margin, that is to say, maximize the distance between the discriminant and these support vectors. So this is a simple problem in theory. We want to maximize the distance to the closest vectors, but it's not computable in this way with numerical methods, because when you change the direction and the position of the discriminant, you can change which points become the closest ones. And that causes discontinuities in the derivative of the function, so numeric methods cannot solve this problem directly. The solution involves quite a bit of math that I'm going to skip, but it's basically we're trying to minimize the size of the vector by while imposing the constraint that the margin must be at least 1. So these are arbitrary units that we can and we can increase this value as much as we want if we increase the length of this vector here. But at the same time, we are trying to minimize the length of the vector. So we want the vector to be as small as possible while keeping for every point a distance of at least 1 to the discriminant. So this is a constraint that applies to every point in our training set, and we want to keep them all at the distance of at least 1 and then minimize the vector. So this is what makes the discriminant try to move as far away as possible from the closest points to allow us to have a smaller vector here, while at the same time still respecting this constraint that the distance to the margin is larger than 1. Okay, so this is a constrained optimization problem. We are optimizing this subject to a large number of constraints, one constraint per data point in the training set. And this can be solved with Lagrangian multipliers, which allow us to write this as just an optimization problem by multiplying the expression that we're trying to use here as a constraint. So I'm not going to detail that part, just jump quite a long set of steps in the mathematics here. But what this comes down to is this particular problem. So we want to maximize the sum of these Lagrange multipliers, and these are multipliers that apply to each of these constraints. So we have one of these for each data point in the training set. And we want to maximize the sum of the multipliers. They are all 0 or larger, minus this expression here. And this expression is the sum of the products of all the pairs of points, where we have the inner product between the two vectors, the 2 points, the product of their classes. The classes can be -1 or +1, and the product of their respective Lagrangian multipliers. So the intuition here is that if we have 2 points that are close together and belong to the same class, so this is either -1 times -1 or 1 times 1, so this will be +1. If the points are close together, their inner product will be +2, and so this will be positive. Since this is a penalty applied on what we're trying to maximize, then if the points are close together and belong to the same class, the optimal solution here will be to bring their Lagrangian multipliers to 0. But if the points are close together and belong to different classes, then this term will be negative, and now we will have minus some negative value, so this will actually be a bonus. So when we have points that are close together but belong to different classes, the tendency will be for the Lagrangian multipliers to go higher in order to increase this overall expression. Now we have these constraints. The sum of the Lagrangian multipliers multiplied by the classes must be 0. So the total Lagrangian multipliers on class 1 must be the same as that on class -1, and they all must be equal to 0 or larger, so non-negative. So the idea here is that when we have points that are close to points on the other class, their Lagrangian multipliers will tend to go up. But if the points are just surrounded by points of the same class, then the Lagrangian multipliers will tend to go to 0. And this helps us identify the support vectors. The support vectors are the ones that have a non-zero Lagrangian multiplier. So in this case, we have these 3 points with alphas greater than 0, and all the rest will have alphas of 0, because they don't really matter for where the frontier lies. So this works well if classes are linearly separable, but if we have classes that are not linearly separable, then we'll have many points that are in different classes that are close together, and at some point the Lagrangian multipliers for points in one class and for on class 1 and class -1 will shoot towards infinity, and we will not have a maximum for this expression because the expression can be infinitely large. So when we have classes that are not linearly separable, for example like this, then we don't have a solution to this problem. We cannot find a set of alphas that maximize this expression because everything just shoots to infinity. So in this case, what we can do is to, the reason for this, by the way, is that we cannot respect the constraint of having a margin of at least 1, because the margin will go down to 0 or even less, because the points will now fall on the other side of the frontier, and we cannot, no matter how large the parameters are, the vector of parameters, we cannot respect that original constraint that we had here, that for all points the margin must be at least 1. But what we can do is to add some slack to the margin. So instead of just requiring absolutely all points to have a margin of at least 1, we can say that we want them to have a margin of at least 1 minus some slack that we can create for each point, that if it's larger than 0, then we are entering the margin, so we are subtracting from this distance to the margin. And if it's larger than 1, then we can even be on the wrong side of the discriminant. So we're actually on the wrong side of the frontier between the classes. But now we want these also to be as small as possible. So we want to minimize the size of the vector of our parameters, and also minimize these slack variables that we had here with a weight of c. So this basically is the regularization factor that we are giving here. It's a penalty on how the margins are being violated. So if c is very large, we are putting great emphasis on the violation of the margins. We don't want the margins to be violated. If c is small, then we are allowing the margins to be violating and prefer to just minimize this vector here. So again, there is quite a lot of math now going on here, because now we have also Lagrangian multipliers for the margins and so forth. But eventually, what it comes down, it simplifies to this. This is exactly the same expression that we had here, with one small difference, is that now there is an upper bound for the Lagrangian multipliers for our data points, that they must be greater 0 or greater, but they cannot be larger than c. So we can think of this regularization factor as setting an upper bound on the penalty that we can give for violating the margin. So now this will no longer shoot to infinity, because even if there are violations of the margin, the alphas for those points will stop at C, and we can now solve this kind of problem. So regularization allows us to have some violation of the margins. Now the discriminant lies here. There are some support vectors here that lie exactly at the margin, but then there are others here shown in red that are penetrating the margin. And so we can see that if we look at the actual alphas that are computed for this case, we see that most of them are effectively zero. So when you have 10 raised to the minus 15, minus 14, and so on, all these are in practice zero. This is just small rounding errors. Then we have these here that are not zero, but are still below C. I use the C of 10 in this case. So this one is 6.7 approximately. Then we have another one here, 2.5, and so on. And then we have these that are exactly 10. So these maximized the penalty, and these correspond to the red ones that are penetrating the margin. Okay, so this is what is called soft margins on support vector machines, because we can allow the margins to be softer, to be penetrated by the points. And this allows us to now solve a problem of trying to separate classes that are not linearly separable. We will have some errors here, but we still have a solution. Now, this solves the problem of finding a solution when the classes are not linearly separable, but it's not really good if we have something like this. So if we have frontiers that are very far from linear, if we try to solve it just with soft margins, we can get a solution, but this is a very poor classifier which does a lot of mistakes here. But we can use that trick that we saw with logistic regression of increasing the power of the classifier by expanding our data with nonlinear transformations into higher dimensions. This we did by hand with logistic regression, but with support vector machines we can use the kernel trick. Okay, I'm going to explain this trick that comes from the fact that what we are maximizing is an expression of these Lagrangian multipliers that we're going to try to find, and the inner product of pairs of points in our data set. A kernel function, in this sense, we already used another meaning of kernel function previously when we were looking at kernel regression. So it's unfortunate that mathematicians reuse the same expression in different contexts, but in this context it means something completely different, which is a kernel function of two vectors gives us the inner product of the vectors resulting from some transformation applied to each of the original vectors. So looking at this may not seem very useful, but this is particularly useful when the kernel function is much simpler to compute than the actual transformations. For example, suppose that we have this transformation here that takes a vector x that is composed of two features, x1 and x2, and builds this vector that has all these features, which are 1 square root of 2 times x1, square root of 2 times x2, then the product of the two, the square of the first one, and the square of the second feature. So computing all of this is actually much more costlier than just computing the inner product of the original vectors, adding 1 and squaring that. But it's the same thing. If you do this transformation on vector u and then do it on vector v and compute the inner product of these resulting vectors, you get the same result as computing the inner product of the two vectors, adding 1 and squaring. So this is a good kernel function to replace these transformations if all we are interested in is the inner product of the vectors. which is what happens to be the case with support vector machine. All we are interested in is the inner product. So in general, this polynomial kernel allows us to do expansions to any degree n by simply taking the inner product of our vectors, adding a constant, and raising to the power of n. So this does implicitly the inner product of these transformations that can be very large. So what the kernel trick, the way we apply this on support vector machine, is to replace these inner products with the kernel function. So this makes it implicitly as if we were transforming the vectors using those transformations into a higher dimensional space and then computing the inner product in that dimensional space. But we do it for free or nearly for free because these kernel functions are much simpler to compute. Okay, now so to classify and so on, we don't actually compute the discriminant because the discriminant now is in much higher dimensional space, but we can still classify just by looking at by using the same kernel function and by looking at the sign of this expression. So basically what we are doing here is we are turning that task of transforming the data non-linearly into a higher dimensional space into this implicit kernel trick that just gives us the result of the inner products after the transformation, and we don't even have to do the transformation explicitly. So let's see an example using a polynomial kernel. We can choose the coefficient, the degree here. The degree is the n over here. This coefficient 0 is this constant that we add here. And now we can try different degrees. And you can see here, so this is a polynomial kernel of degree 2 that now gives us this curve because we are still doing a linear classification, but we are doing a linear classification implicitly on that higher dimensional space after doing an expansion like this. And this is an example of using the C value of 1. So we are using strong regularization by allowing many points to penetrate the margin because the maximum penalty we give for that is just 1. We can increase the degree of the polynomial, and we increase the ability of the discriminant to curve in this two-dimensional space. Actually, we still have a linear discriminant, but it's now on a much higher dimensional space after these transformations. And if we increase the value of C, we increase the penalty given to points that penetrate the margins. So we're actually reducing regularization. We are forcing the discriminant to adjust much tighter to the data that we have here. This is an example with degree 3 and C of 1000. We don't really allow any penetration of the margin. So now we only have we have this frontier, and we only have points that lie on the margin that are the support vectors. There are other kernels that we can use. For example, this radial basis function kernel using a Gaussian function actually does an implicit transformation to a space of infinite dimensions, and it is based on the distance between the points. So this is the expression for the kernel. We can use this gamma to give to scale the distance. So if we increase gamma, even small distances will now cause this function to decrease very steeply. If we decrease gamma, we increase the neighborhood where the points will still have an effect here. So you can use this with the RBF kernel, and these are some examples. For example, a very small gamma makes this function here, this exponential function, decrease slowly with the distance to the points. So actually it makes us look or feel the effect of many points in the neighborhood at each point we are trying to classify. If we increase the gamma, we start looking at narrower and narrower neighborhoods. So we start increasing the power to curve the frontier here. Also, if we have a very low value of C, we are doing high regularization by allowing many points to penetrate the margins. If we increase C, then we are tightening the margins here. And so by playing with the regularization factor, the C and the gamma, we can adjust the power of the model, and also using regularization, we can, if we are overfitting, give some margin, soften the margin so that the frontier is not as intricate, and we can reduce a bit overfitting. So these are some examples. Now, one thing that I must note, I will try to put maybe in a couple of weeks some exercises for this, but in this case, I'm not showing you the whole code because these plots are a bit trickier to do. So I can share the code with you later, but I didn't put it here in the lectures. So basically, when you do something like this and you fit, you just have the classifier. You can predict the classes of new points, but this by itself does not give you the plot. So if you try this code, you won't be seeing the actual visualization. But in general, this is something that is not useful because this only works well for 2 dimensions. If you're solving some practical problem, more realistic problem, you will have more than 2 features, so then you will not be able to visualize the classification like this. So this is just to help you understand what is going on with these parameters. Okay, so to sum up, we saw logistic regression. This is a linear classifier because even though we are computing a regression to the probabilities of belonging to each class, which is a continuous value, we then use a threshold on the probabilities to split the space where our parameters or where our data lies into different regions to classify. This is a simpler model because it's a linear model, and it's easier to interpret than support vector machines with the kernel trick because you have one coefficient for each feature, and you can even get an estimate of how important each feature is for classification and so on. With the support vector machine, if you use the kernel trick, then you have very powerful models because you are doing this implicit nonlinear transformation, nonlinear expansion into higher dimensions. However, this makes the model then harder to interpret because we are not even seeing the actual discriminant. It may be in a space of infinite dimensions, and so we don't have those clean coefficients associated to individual features that logistic regression gives us. However, support vector machines are very powerful models if you have harder data to classify, so data that is not as easy to classify, and you have these different kernels, the parameters of the kernels, and the regularization that you can adjust in order to try to find the best compromise between having more power and reducing overfitting and so on. So in both cases, in scikit-learn, you can use this C parameter for regularization, and the convention is that a lower value of C makes the regularization stronger, so it simplifies the curvature of the discriminant, and it pushes the discriminant away from the points. If you have a higher value of C, then the discriminant will will ignore points that are further away and try just to avoid the points that are close to the frontier. So basically, if you have a high regularization, for example, like this, then the discriminant is trying to get away from points that are farther apart, that penetrate the margin and so on, and it tends to get simpler here. If you have a large value for C and very low regularization, then the discriminant is just zigzagging, looking at the points that are very close by and ignoring everything else. So you tend to get more overfitting if you use weaker regularization. And this is true both for logistic regression and support vector machines, although since logistic regression is a linear classifier, you generally only have problems with overfitting if you have many features. With support vector machine, it's easier to have problems with overfitting because you can use the kernel trick. Okay, so that's it for now. We can talk about this on Thursday on the live session.